orbiter to carry humans into space in the historically important STS-1 mission in 1981. So I'm going to jump back in time a little bit from her first manned spaceflight. It is 1977. The Space Shuttle program is well underway, just 5 years after its initial announcement in 1972. The first test flight for landing and gliding was being run in the Enterprise space shuttle. Although the first shuttle, Enterprise wasn't actually capable of spaceflight, but Honor was already under construction, and it was to be the Columbia orbiter. Columbia's manufacturing had begun in 1975 in Palmdale, California, at the Rockwell Assembly Line. She would be transferred to Kennedy Space Center in 1979 in preparation for the orbiter's first flight into space. Unfortunately, it would be delayed by 2 years when issues arose about the shuttle's thermal protection system and its engines. But success would strike in 1981 with STS-1's 54-hour mission, manned by Commander John W. Young and pilot Robert L. Crippen. Now, I just mentioned the thermal protection system, so it's probably best I talk about that subject next. How not to burn up on re-entry. So, when an item re-enters Earth's atmosphere, it experiences a thing called atmospheric drag. So, as masses say themselves, drag is generated by the difference in velocity between a solid object and a fluid. In our case, the fluid is the air the object encounters upon re-entry. Due to the high speeds of re-entry, in the shuttle's case 17,000 miles an hour, the mechanical friction of the vehicle to the air causes aerodynamic heating. This heating is enough to disintegrate an object. This is the reason why small asteroids are harmlessly destroyed upon entering Earth's atmosphere. But if you go into space and want to come back again,
there's a 5-minute slowdown caused by a crash on US Highway 19, south in 2 miles. You are on the fastest route. You should reach your destination by 8:34 a.m.
techniques, depending on its location. This varies in protection requirements, from 371 degrees centigrade, or 699 degrees Fahrenheit, to over 1280 degrees centigrade, or 2336 degrees Fahrenheit. So I won't go into all of the installation, and instead I'll just talk about the materials used to protect the shuttle to temperatures over 1280 degrees centigrade, such as the nose cone and the leading edges of the wings. This was a material called reinforced carbon. This part of the shuttle's TPS is a composite made up of carbon fibre reinforcement in a graphite matrix. These were great at protecting Columbia from the insane heat upon re-entry. But like all things, this performance came at a cost, and that was its impact resistance. True, the carbon was more resilient than the famously brittle, high-temperature reusable surface insulation tiles, which was used elsewhere on the shuttle, but it still wasn't the most impact-resistant. This was an issue after STS-1, with Columbia losing 16 tiles, with 148 others sustaining some sort of damage, as noted in the Accident Investigation Board report released in 2003, from excess solid rocket booster ignition pressure. You see, the shuttle's project design requirement was to set out that no debris would be allowed to hit the orbiter, for the reason of the fragile TPS. And it would turn out that no greater culprit of debris on a launch stack was that of the Space Shuttle external tank. This was because of its foam insulation. This was vital, as it kept the tank's fuel contents at a required temperature. The insulation was applied to the external tank via a spray. The ramps that attached the struts to the external tank to the shuttle were also covered in foam insulation. During the early launches, it was found that in almost every case, some form of the foam insulation could become dislodged and become a stack launch. However, even though design requirements meant that foam sheds should not be a thing at all, and in a very natural response, became thought of as less and less an issue as subsequent shuttles were not lost to foam impact damage. Interestingly, it was even thought